First, I want to make some corrections to last lecture, some things that I said that could be misleading, and a couple that were actually notationally incorrect. All of these were actually responses to questions, and so I think y'all knew something was going strange. First of all, Newton-Raphson. Someone over here asked me what's the difference between Newton-Raphson and Newton? Maybe they're gone. Yeah. The difference, when you're talking about maximum likelihood, I thought they were asking a different question. But anyway, when you're talking about maximum likelihood, Newton and Newton-Raphson are one and the same. But there's also a procedure called Gauss-Newton that you've come across in nonlinear least squares. And it has the kind of same form as this. So they're both derived from Newton, but one applies for maximum likelihood, one for nonlinear least squares. And just to keep the two separate, we call Newton-Raphson and then Gauss-Newton for the two. It's just nomenclature. Second, this one I think a couple of y'all were talking about. What if we're doing Newton-Raphson and the Hessian is, or the negative of the Hessian is not positive definite, so you're not guaranteed to get a rise. Why don't you just go in the opposite direction? And that's indeed what you can do. When the question was first asked, I got confused about semi-positive definite as opposed to negative definite, and got into this issue about whether it's singular or not. That's a separate question than what was actually asked. You can actually look at this. You don't even have to test whether it's positive definite or negative definite. If you do a Taylor's expansion on the log likelihood at the new parameter values, just do a first order Taylor's expansion. It's important to recognize this only is going to work within the neighborhood that's close enough to your current value to have the slopes be all that's relevant. First order Taylor's expansion. Oops. Okay. And now for Newton-Raphson, we know that the step is this. The scalar, and then I always put the negative of the Hessian inverse here instead of putting the negative out here, because we replace this with other things later. But you want this thing in parentheses to be positive definite usually, times gt. Okay, so if we substitute this in, take this over here, we can substitute that in there. And you get all of this primed, okay, which then, just rearranging terms, so the prime will bring this out here, and then since this is symmetric, you don't have to bother about whether to transpose it or not. So essentially, if this thing's positive, if this is a positive definite matrix, then, or if this product here is positive, no matter what the thing, there, then this is going to rise for a small neighborhood. So what you can do is just calculate this value here. If it's positive, you go in the direction you normally would. If it's negative, you just reverse it and go in the opposite direction. And this is our convergence criterion. So you're calculating it anyway. So you might as well just calculate it right at the first. If this convergence criterion gives you a negative value, you go in the reverse direction. If it gives you a positive value, you go in the direction you were planning to. This is if you're using Newton-Raphson. You actually very seldom use Newton-Raphson. The big problem is not this issue of whether negative Hessian is positive definite, because you can solve it by going in the opposite direction. The big problem is that the Hessian's just extremely hard to calculate time intensive to calculate when you've got a lot of simulations going on. So whoever was saying this, a couple of y'all did. Do you remember who it was? Marta mentioned it. Oh, weren't you the person who asked about Newton-Raphson versus Newton? Well, I answered it before you walked in. Newton-Raphson and Newton are used interchangeably as names for when you do maximum likelihood. But when you do nonlinear least squares, minimizing the squared difference, squared errors, there's another procedure that's very similar that's called Gauss-Newton. And so to distinguish those two, you don't just, if you said Newton, it's possible that people could think you're referring to the wrong one.
I still wonder what Raphson added to Newton.
I don't know. I think my understanding is that he was the person who derived the idea of applying this to maximum likelihood, where the Hessian becomes a relevant thing. Okay, and then last, and this is an actual mistake last time. Someone asked about, now don't you divide by n? And I very quickly said, well, it just cancels out. I don't know when you asked that. Who asked that? Yeah. I don't remember when you asked it, but it did key in my mind that something's not canceling here. And in fact, I gave the stuff wrong. So when you're doing the standard errors for your estimate, the standard errors are actually negative h, the inverse of the negative of the Hessian inversed, or if you're using the information identity, then it's that. It is not that quantity divided by n, which is what I said last time.
You know that I went back to my paper and I divided everything by hand. In another paper, a completely different one. I said, oh, I have everything wrong.
You got it all wrong? Well, you have to be really clear about this, because this is correct when you use the notation that I used last lecture, for where h is the derivative, second derivative of the likelihood function, not divided by n itself. Often the notation that is used for proofs, actually, when you're proving the asymptotic properties, you don't use h as I denoted it. You use, in a sense, the average Hessian in the sample. And so you divide by n, and then you have to correct for that in your formula for the standard error. So you need to go back and check your paper and see which h you used throughout.
I don't use n because now everything was very strange. So I was like, ooh.
So you realize, okay, good.
I use an n
and with misspecification, the standard error becomes without an n in there again. So this should make sense, because what this Hessian is remember the log likelihood is the sum over n of the probability for each person. Okay. So then the Hessian is the sum over n of the second derivatives of these things. Okay. And as you increase sample size, this sum gets bigger, because you're just adding more elements to it. Okay. So since that's getting bigger, the inverse gets smaller, and your standard errors get smaller, as you'd expect them to. If you then divide this by n, like I said last time, you're essentially taking the same effect twice. This is getting bigger, or you're counteracting that effect is what you're doing. Right. Okay. A lot of people, though, in proofs will, instead of using this, will use h, like what we might call bar, which is 1 over n. And then you have to change this formula to account for that. Okay, so to be consistent with what I did, you need to use these formulas. That is indeed what's in the programs. Hopefully you checked that. And but then when you're comparing it to what notation is used in proofs, often you want to account for the fact that what we're using as H and G is not normalized by sample size, and often those proofs do normalize by sample size. So you got to watch where the ends come through. Okay, were there other things that, those were the three things that I remember from last lecture people asked questions about and I got kind of didn't give good answers. Anything else? Good. So, the problem set. First of all, some of y'all got your accounts zapped by Grace because of various things. If you have, you should go talk to her and get your account reinstated. You shouldn't feel bad about this. I've already talked to her about it. It's very easy to do things that mess up the system if you're not too sure how to do things right. I do it all the time, and it's not malicious. It's just because you don't know how to do things well. There's three problems that seem to be arising. One, orphan, what Grace calls orphan jobs. If you run a job in batch and then go and do something else on your computer while it's running in the background, if it's got like an infinite loop in it or something, it'll just run forever and never stop. So you should definitely go check it periodically. If you think it should take 10 minutes to run, go check it after 10 minutes and see what's happening. We had runs that were running for 48 hours. And none of the jobs that we're doing here take more than 5 or 10 minutes. So you should have a sense of how long these things are going. They eat up the system, So what Grace did was just go in and kill those jobs and then disable the account so you wouldn't do it again. So that's the first thing, is if you're running things in the background, go look at them periodically to see what's happening. It's very easy to get infinite loops going. Apparently this can happen also. I'm not absolutely sure of this because I've never tried it. But if you're working in interactive Gauss and are running a job, like you do a run job name, and then kill the Gauss job, it does not kill the Gauss program that you're running. It essentially kills the Gauss shell, but not the program you're running. So you should kill the, you should, if you're running, if you do Gauss Lab and you've got your Gauss command thing up here, it's got a little kill up here and then a quit. Before you quit Gauss, you should kill the job you're working on, okay? And then quit. Otherwise, if you just quit, it doesn't kill the job and it keeps running in the background.
Is there a way to tell where you are in your program?
Not without killing it. When you kill it, it'll give you the line it died on.
Display, like in MATLAB, you can just display where you are.
I don't know.
With this, I'm doing this.
I am doing it. I don't know if there is. Is there?
You can check what you're an owner of, what jobs, by typing PS space EF space and pipe, your grep, and then your username. And it will give you all the jobs and the status of them and where they are and how much they take up.
But that won't tell you what you were asking, which is what line of code is the job in.
That's a different thing. But you can see how long they've been running.
You can see how long they've been running.
Print a number and
But
it'll transfer.
it didn't really do it for us, right? We were doing print.
In MATLAB, you can do display.
Yeah, in
put the
Gauss we
message.
couldn't figure it out.
But y'all can help each other on this. I'm truly not a very, I use econometrics all the time, but the issues of system maintenance I'm pretty naive at. And, this is why I do things at home on my own computer, so I don't have to deal with this stuff. I'm sorry? How to kill it? Yeah, how do you kill a job in Unix?
Type PS and then you see your jobs. And
Right.
then you say kill and there's a job ID.
There's a job ID that's giving,
Kill and then the number.
Right.
You were saying a lot of things after here. Okay.
If you type PS, will give you just the current jobs, but if you want to have all of your jobs, you type PS space EF space
E what?
EF. Oh, there's a dash before EF. And then space, and then pipe, so like the line, yeah, a space, grep, and then your space username.
You don't have a bench,
Grep. grep, G-R-E-P. EP.
Grep. Whoever came up with this stuff?
Grace actually.
Grace made all these up? We're all slaves.
It will give you like whether it's in temp space, whatever directory, whatever.
Right.
There isn't a batch
Type
command.
kill space dash 9 and then job number. That will kill it. Sometimes they kill it.
So you need to kill space 9 or slash, what is it? Dash 9, and then your job number. Okay.
Why dash nine?
Is it EF or EF?
Why dash nine?
This is EF.
Sometimes it will kill it properly.
Okay.
Kill 9 will definitely kill it.
This is the way people learn these days. You know, I think it's amazing. We've moved to a system where, when I was growing up, you had a program manual, and you'd read the manual and could read. And now it's gotten to where there's so much stuff, no one learns that way. You always learn by word of mouth, kind of figuring out. It's a very sweet kind of way of thinking about our system nowadays. You know, we're back to like the old days where it's an oral tradition again. Like Homer, you know. We all tell stories. Okay, the second thing is temp files. I don't know how this happens, but Gauss will, if you're creating a lot of data, Gauss reads things in and out of memory and will put things in a temp file when it's not using it. Okay? None of the programs that we were doing create tremendous amounts of data, but somehow 4 or 5 people created huge files in temp files. Now, does anyone know how that happened? What was going on?
I think Grace emailed you about a couple of people. Well, when I went to different Emily's and looked at temp space, there were many more than just a couple. It seems like almost everybody created them, and Grace only went after a couple of people.
Well, why? How could it possibly have happened?
It says something that basically when you, this is some allotted amount of space that when you run Gauss, you sort of, it automatically allots you some space. That's what it seems to be doing. So
whether you use it or not?
whether you use it or not, yeah. So it's not that we generated them per se. Gauss just automatically.
Okay, well let me check on that, because I don't remember ever having run into this problem myself, but it might be just that Grace doesn't disable my account when I fill up the temp files. Okay, but they were huge. I mean, they were truly enormous. So I don't know, it would be crazy for Gauss to do that. Might be a problem with the new Gauss we've got for this class. And then last, you need to nice your jobs. You know, does everyone know how to do that? No? Okay. This means you put it in a priority queue so it runs and lets you do nice. And then you put a plus and the number, and the bigger the number, the further in the back it goes, the lower priority. So +1 gives you the very highest priority. +12 is a kind of nice number to put. And then Gauss Lab. So it's the program. Your file name. This is the job you're wanting to run in Gauss. And this is the priority you're giving yourself. A high number means low priority. Another one of those bizarre things. And yeah.
What's the minus B for?
I don't know what the minus B's for. I always just put it. Batch. Okay. Again, these things, I've just learned how they work and just keep doing the same thing over and over and over. So,
If you don't put the B, it starts up a little Gauss window.
Right. So it doesn't run it in the background.
Right.
So maybe it means not batch, but background. I thought that's what the ampersand did, but.
No, that brings you back.
Oh, okay. So that was just computer administration. Had nothing to do with our jobs itself, our, actual learning experience. So, let's get into this. Everyone ran job 1. Happy with it. So now, did you reran it, the same job, using a different algorithm? Did anyone find any major differences between these algorithms? Taking longer or ending up not at the same point? Which ones seem to take longer? Yeah?
Ross was the shortest.
Yes, okay, what I did, when I got Davidoff Fletcher Powell, that definitely took the longest. It took 2 or 3 times longer than the other ones, and it took 12 iterations, which is like 3 or 4 times many more
It
iterations.
was also like a little bit off the other ones by about 1% of the total.
Right. So in this case, Davidoff, Fletcher, Powell didn't do particularly well. What were you saying?
Newton-Raphson was 3 iterations only.
Newton-Raphson was the quickest in terms of iterations, but not the quickest in terms of time. It's interesting because and that would make sense. Each iteration of Newton-Raphson